A few words regarding generation mechanism. Generation of whole free electron pairs in semiconductors. Let us consider silicon or germanium semiconductors to explain, to understand the process of generation. These materials are tetravalent. There exists 4 electrons in their outer orbits. These 4 electrons, they are not free. They are in covalent bonds, 4 covalent bonds. They are bonded. Therefore, they cannot contribute to flow of electricity. They are not free, but they can be made free. They can be ejected out of their bonds, covalent bonds, by supplying energy. Whatever may be the form, electrons require energy to become free. Once an electron is supplied with energy necessary to come out of the covalent bond, then it comes out of the bond, becomes free, leaving behind a vacant slot in the covalent bond. This vacant slot is called hole. It is found holes act effectively as positively charged electrons. They also contribute to the flow of electricity to increase the electrical conductivity as much as electrons, free electrons. So point is, free electrons, holes, come into being. As a result, conductivity of the slab goes up, flow of electricity becomes more easy. So generation leads to more current in the slab. From energy band theory point of view, generation implies electrons moving from valency band to conduction band. An electron in conduction band means it is a free electron. Only free electrons are capable of contributing to the conductivity. But to enter into conduction band from valency band, electrons require a certain amount of energy. As already mentioned, this energy has to be supplied in one form or other form. Electronic devices, semiconductors, part 4, series on semiconductor devices and circuits, lecture number 1.14. The behavior of electronic devices like PN junction diodes and transistors depends upon the nature of semiconductors that go into their fabrication. In this session, the focus is on variation of conductivity in semiconductors by doping, that is, by the addition of impurities. Doping increases carrier concentration. If it is with N-type impurities, electron concentration goes up. If doping is with P-type impurities, hole concentration increases. In either case, carrier concentration rises, leading to increase in the conductivity. We focus here in this session on how doping is able to increase carrier concentration and also upon Fermi energy. Fermi levels get affected in the energy band diagrams of semiconductor materials when dopants are added. Now let us move further to begin the course session. We begin the session with a small discussion where it is explained how doping is able to create more charge carriers in semiconductors. Two diagrams are given, A, B. In A is shown how free electrons are created by doping. In B is shown how holes are created by doping. In both A and B, silicon semiconductor is considered. In A, impurity atoms are antimony material. It has 5 electrons in its outer orbits. When antimony is added to silicon, some of the silicon atoms get displaced by antimony atoms. Here is shown one such antimony atom. Notice this atom is surrounded by silicon atoms. Out of 5 outer orbital electrons, 4 goes to occupy the vacancies left in the covalent bonds by the displaced silicon atom. 1 remains outside the covalent bonds. That electron is shown here. As it is outer orbital electron, it is loosely bound to the antimony atom. Because of this loose boundedness, very little energy is required to detach it from its parent atom. Once detached, it is almost free. It is free. Even while it is attached, it is almost free because it requires very little energy. That energy is anyway available in the surroundings. Surroundings carry energy in the form of heat. That energy is sufficient. So one antimony atom, we can see, it is creating one free electron. If we add more and more number of antimony atoms, impurities, more and more free electrons comes into being. So electron concentration, free electron concentration goes up. Now come to B diagram. Here also we considered silicon semiconductor. In this case, indium impurity is added. Impurity indium is trivalent, so 3 electrons exist in its outer orbits. These 3 electrons occupy 3 vacant positions in the covalent bonds that are existing when silicon atom leaves are displaced by the indium atom. Here is shown indium atom is surrounded by silicon atoms. Outer orbital 3 electrons of indium occupy 3 vacant positions in the covalent bonds, and one vacant position is left as it is after displacement. This vacancy is called hole. So addition of indium brings one hole into being. Hole is also charge carrier. It is also a partner, a factor in increasing the conductivity. So we conclude to go further. In A is shown that addition of antimony pentavalent impurities creates electrons in the semiconductor. Addition of trivalent impurities like indium generates holes in the semiconductor. Increase in electron concentration or hole concentration leads to increase in the conductivity of semiconductor. Therefore, one can conclude by the process of doping, one can increase the conductivity of a semiconductor material. Now, addition of impurities makes results in some changes in the energy bands of the semiconductor material. This particular aspect is considered in this slide. When a semiconductor is doped, it acquires additional allowed energy levels in its energy band structure. Donor type impurities just below EC at a level usually denoted by ED, and acceptor type impurities just above EV at a level usually indicated by EA. Energy levels EA and ED can be interpreted as the maximum energies that can be had by any electron of valence or conduction band when the impurities are p-type and n-type respectively. What he is trying to tell is, to understand, consider the energy band diagram of intrinsic semiconductor. This is conduction band, this is valency band. In between, band gap energy is there. Band gap. This is band gap. Notice energy of any electron. It can be in conduction band, it can be in valency band, but it can never be in band gap. It is forbidden for the electrons to have energy that falls in the band gap. So to move an electron which is in the valency band to conduction band, we have to give energy at least equal to band gap energy. Then only valency band electron can move to conduction band. Or when conduction band electron falls into valency band, an energy gets released which is at least equal to band gap energy. Now, the point is, conductivity means, or increase in conductivity means, valency band electron moving to conduction band, and it requires energy equal to band gap energy. If this band gap energy becomes small, then there is more possibility for a valency band electron to move into conduction band. If it is made less, and if it is made 0, then valency band joins with the conduction band, and maybe majority of valency band electrons move into conduction band, thereby increasing the conductivity tremendously. So here the point is reduction in band gap, forbidden band gap. It increases the probability of valency band electrons moving into conduction band, thereby increasing the conductivity. Addition of impurity atoms, that is doping. Doping, in fact, it reduces forbidden energy gap. When donor type impurities are added, an allowed energy level is created just below EC. The conduction band electrons even can have energies just below EC. This is EC, this is ED. Notice impurities led to reduction of band gap by certain amount. It is equal to gap between EC and ED. This is ED. There is a reduction of this much. Similarly, if we add acceptor type impurities, allowed energy levels come into being somewhere here just above valency band. If this is EA, allowed energy levels come into being, and these energy levels are indicated by EA. Now notice, with the allowed energy levels lying at EA, band gap energy or band gap is reduced. Reduction in band gap means increase in conductivity, increase in the possibility of electron moving from valency band to conduction band. So this is a way of explaining the increase in conductivity of semiconductors by addition of impurities with the help of energy band diagrams. Energy bands. Energy band diagrams of N and P semiconductor. This is conduction band. Bottom edge is indicated by EC. Valency band is at the bottom. Its upper edge is indicated by EV. EC minus EV. This energy band is forbidden for electrons. This gap is called forbidden energy gap. It is indicated by EG. This is the case of intrinsic semiconductor. Now we consider N-type semiconductor. Everything remains the same as intrinsic semiconductor, but notice one energy level, extra energy level is added just below EC. It implies that an electron can have energies that lie in between EC and ED, in addition to the energies represented by conduction band. Okay. Net effect is reduction in the gap, band gap. Similarly, in case of P semiconductors, energy band diagram is same as energy band diagram of intrinsic semiconductor, except one difference, that is a level, energy level is added here. This energy level is, allowed energy level is indicated by EA. Presence of EA reduces the gap. Reducing gap means, as already mentioned, more possibility for the valency band electron to jump to conduction band. Reduction in band gap means lesser and lesser energy is required for a valency band electron to move into conduction band. Both imply increase in conductivity. So through energy band diagrams also one can explain, one can understand why conductivity increases with the addition of impurity materials to an intrinsic semiconductor. We move to another aspect of semiconductors. It is Fermi function. What is Fermi function? For understanding's sake, consider a semiconductor. It may be intrinsic, it may be extrinsic, it doesn't matter. Inside several electrons exist, plenty of electrons. If it is at a temperature above 0 degree Kelvin, let us suppose the slab under consideration is at room temperature, so electrons. These electrons, they have different amounts of energies. All electrons do not have same energy or equal amount of energy. Each one has its own energy. Fermi function gives energy distribution of electrons inside a semiconductor. With this small introduction, now let us move further. Fermi-Dirac distribution function, or Fermi function in short, is a probability function f of E. E stands for energy, which gives the probability that a quantum state with energy E is being occupied by an electron. It describes the arrangement of particles as per their energy and is given by this expression f of E equal to 1 by 1 plus e power E minus EF by kT. EF means it is a parameter, Fermi energy. T means temperature. K is Boltzmann's constant. Here EF is an energy level known as Fermi energy, as already mentioned. The probability that an energy state at E is empty, not occupied by an electron, or equivalently occupied by a hole, is equal to 1 minus f of E. So Fermi function is electron energy distribution function. Whole energy distribution function can be had by subtracting it from 1. Some important points regarding Fermi function. The Fermi function is absolutely symmetric about EF. EF stands for Fermi level, Fermi energy. At absolute zero, the Fermi function f of E is a step with a transition at EF with f of E equal to 0 for E less than EF and f of E equal to for E more than EF. At any other temperature, the Fermi function f of E is equal to half at E equal to EF. The carrier concentration depends upon f of E and n of E. N of E is density of states function. The actual density of states N of E at conduction and valency band edges is exactly 0. In conduction and valency bands, N of E varies parabolically with E. Fermi function, Fermi level, these are important parameters. They give an empirical relation for carrier concentration in terms of energies. Carrier concentrations on their own, they influence the conductivity. Hence, conductivity is ultimately dependent upon Fermi function and Fermi energy levels apart from other parameters. So they have certain special significance, Fermi function and Fermi level. That's why they are being mentioned here. Here is shown Fermi function in A at 0 degree Kelvin, absolute 0 degree temperature, and at other temperatures too. At 0 degree Kelvin, you see it is a step. For T1, it is like this. For T2, which is more than T1, is shown with the dot dash line. In B is shown density of states function on horizontal axis and energy on the vertical axis. Above is conduction band, below is valency band. The curve in the conduction band, it is proportional to square root of E minus EC. The curve in the valency band is proportional to square root of EV minus E. Some more points regarding Fermi energy. Fermi energy represents average energy of the electrons. It is also maximum energy of any electron at 0 degree Kelvin. The first definition, first statement, first bullet point gives a beautiful definition for Fermi energy. Beautiful in the sense it gives an understandable meaning to Fermi energy. Fermi energy is useful to calculate carrier concentration and transport in semiconductor devices. Transport phenomena, analysis of currents in semiconductor devices, it requires Fermi energy and Fermi function. Hence, their importance in semiconductor physics. Fermi levels for various semiconductors are given. For intrinsic, Fermi level is EV plus EC by 2. For p-type, EF Fermi energy level is EV plus KT natural logarithm NV by NA. N-type, EF is EC minus KT natural logarithm NC by ND. The meaning of EV, NV, NA, NC, ND, EC all are already given. Fermi levels for different types of semiconductors are shown. When I say different types, I mean intrinsic, N-type, P-type. In case of intrinsic, this is Fermi level. In case of N-type, extrinsic, this is Fermi. It is not average, it is somewhat lower to ED, lower than ED. In this case, it is above EA. In case of intrinsic, of course, it is average of EC. We are in the middle of EC and EV. In this slide is given certain analytical relations. These relations connect Fermi level with carrier concentration. In case of N-type semiconductor, electron concentration is Nc multiplied by e power minus Ec minus Ef by Kt. In case of p-type semiconductor, hole concentration is Nv multiplied by e power minus Ef minus Ev by Kt. Notice Ef is there. Ef is there in these relations. In case of intrinsic semiconductor, of course, carrier concentration is, this is standard relation, A naught power half T power 3 by 2. T means temperature. E power minus Ego by 2 Kt. E stands for gap energy. With this, we come to the end of the present session. Before closing down, let us recollect the important aspects that are touched upon in the present session. The focus here is mainly on energy band diagrams of semiconductors, intrinsic semiconductors and extrinsic semiconductors. And through those diagrams, we tried to understand how conductivity gets increased by the process doping. We also considered Fermi function, Fermi energy level, how these two influence the carrier concentration, consequently conductivity of the semiconductor. Hope this session is useful to you. We meet again soon in another session with a new topic.